All right, this will be the recitation for week 3 for basic anatomy. Here we're covering circuits, or I should say resistance and circuit flow. The first type that we'll look at is DC circuits or direct current circuit, which the resistance in that type of circuit layout matches cardiovascular resistance through blood vessels. So if we look at this problem, we see we have a 4-battery power supply system where 2 of those batteries, there are 2 6-volt batteries in series and 2 6-volt batteries that are parallel to another 2. We see that we have a branched parallel path, one that has resistor 1 and 2 in series, and another that has resistor 3 and 4 in series, and where they collapse back together at a node, we eventually get to resistor 5. Given this 5-component resistor layout, determine the following sets of information. We're going to care about the current flowing through resistor 1 and 2 because they're on one specific path. Whatever current we have flowing past this node point up here will be the same current flowing through R1 and R2, so we do not need to calculate 2 individual current flows. Similarly, because there's a single path down here with resistor 3 and 4 in series, we'll be able to calculate current that's flowing through both of them. And then, because resistor 5 is on its own path, we can calculate a unique current for that one as well. And for each resistor, we can calculate a voltage drop across each resistor. And let's figure this stuff out. The best thing to do is to slowly compress all of your components. Since we just have a resistor circuit, no other components, we can just focus on collapsing all the resistors into one equivalent resistor. But to simplify our time, if we look at the battery supply, the trick with battery supplies is if you have batteries in series, just add up their values. And then if you have power supplies in parallel, well, the key is that both paths must add up to the same value. And then you can just assume that we have one single path of that value. For example, we have 2 battery supplies in parallel or in series, a 6-volt plus a 6-volt, that adds up to 12. On the second path, we have 2 6-volt batteries on one single path, that adds up to 12. And we therefore have 2 parallel paths that are each 12 volts. So that's as if we had a single battery of 12 volts. So that's how we simplified that battery supply. Now, next thing we're going to look at is simplifying resistors. The best thing to do is look at resistors that are just in series or just in parallel. Well, R1 and R2 are in series, so we can collapse that as resistor 1, 2. Because they're in series, we just add up their resistances, 1/2 plus 1/2 ohm, equaling 1 ohm of equivalent resistance. If we were to replace that entire path with just one single resistor. Now resistor 3, 4, that comes from resistance 3 and 4 that are in series. We add up their resistances together, that becomes 2 ohms. Now we have resistor 1, 2 in parallel with resistor 3, 4. It's a single resistor in parallel with a single resistor. We can now use the parallel path formula, which is the equivalent resistance of parallel paths is the reciprocal of each resistance added together and then raised to the negative first power. So 1 over R12 plus 1 over R34 would become 1 over 1 ohm plus 1 over 2 ohms. That becomes 3/2 ohms, which raised to the first power is 2/3 ohms. And that collapses these 2 parallel paths into a single equivalent path. Finally, now that we have these last 2 resistors in series, we can simplify them into some overall resistance by just adding up their values. So resistor 1, 2, 3, 4, 5 is just resistor 1, 2, 3, 4 plus resistor 5, or 2/3 ohms plus 10/3 ohms equaling 12/3 or 4 total ohms. Now, since we now have our 12-volt battery supply and our total circuit equivalent resistor, we can calculate the current flowing directly out of this battery all the way back into itself. Well, because of our main equation, Ohm's law, voltage equals current times resistance, we can solve for total current by just taking the total voltage divided by our equivalent resistance. That would be 12 volts divided by 4 ohms, equaling 3 amps. Therefore, whenever we have one single path, we know that we have 3 amps flowing through any resistor on that single path. Therefore, we can calculate some relevant information. We know that there are 3 amps flowing through resistor 1, 2, 3, 4, and 3 amps flowing through R5. Because we know that there's 3 amps flowing through R5, we already have I5 right here. And we can rearrange our equation to be voltage drop at resistor 5 is the current flowing through that resistor times its specific resistance, or 3 amps times 10/3 ohms, which gives us a voltage drop at resistor 5 of 10 volts. That gives us the information for resistor 5. Now we're going to need to do some more tricks to get the other resistors parameters. What is key here is that at the voltage drop at 1, 2, 3, 4, this equivalent resistor is going to be the equivalent resistance of 1, 2, 3, 4 times the total current. The only reason we're using total current is because it's still on this single path, this unbranched path, which we know if it's unbranched, it has 3 amps flowing through it. So 3 amps times the equivalent resistance of 2/3 ohms gives us a 2 voltage drop across this equivalent resistor. Because that equivalent resistor was 2 parallel path resistors, we can say that because whenever we have a parallel path with one resistor on each path, the voltage drop across one path must equal the voltage drop across the other path, and that's if we have just a single path of the same voltage drop. Because we calculated in the prior step that this single equivalent path would have been 2 voltage drop, we know that R12 has a voltage drop of 2 volts, as well as R34. So to calculate the current flowing through this path, R12, that would be voltage drop of 12 divided by the equivalent resistance of 12, or 2 volts per 1 ohm, which gives us 2 amps. And that would be our answer for the current flowing through 12. Now the current flowing through 3, 4, that would be just the voltage drop across this entire path from this first branch point to the next branch point, but just looking at the down path now. That is again just 2 volts as we calculated in the prior problem, or the prior slide, and then we'll divide that by the equivalent resistance of R34, which is 2 ohms. That becomes 1 amp, and that gives us our answer here. Continuing on our use, what we know is resistor 1,2 was the compressed resistor of a two resistors in series. What that is to say is, as we have 3 amps flowing from our power supply, 2 amps flow into the top branched path, and 1 amp breaks off and flows into the bottom branch path. Because R1 and R2 are in series, the current flowing through R1 is the same amount of current flowing through R2. So we know that through both R1 and R2, there's 2 amps of current flowing through them. So the voltage drop across resistor 1 is the current flowing through it, which in this case is I12, times its resistance. 2 amps times 1/2 ohm equals 1 volt across voltage resistor 1. And because resistor 2 is in series with resistor 1 and has the same resistance, we end up with the same voltage drop. And that's only because the same current amount is flowing through them and they both have the same resistance. Now, if we look at the down path of resistance 3 and 4, we calculated that this down path had 1 total amp flowing through it. So we know that through resistor 3, there's 1 amp flowing through it, equal as well as once the current continues to flow, that 1 amp will flow through R4 as well. So the voltage drop across resistor 3 is the current flowing through it, 1 amp, times its resistance, which gets us 3/4 or 0.75 volts. And then across resistor 4 would be the 1 amp flowing through that resistor times 5/4 ohms, which gives us 5/4 or 1.25 volts across resistor 4. So things to note is just if you have, and if we were to say add up those voltages across path 1, the voltages add up to 2 volts. Across the branch path 2, the voltages add up to 2 volts. That should be true between any two nodes, any two branch points. The total voltage across one branch path should equal the total voltage across the other branch path. And if we collapse this into one single path, that would be overall 2 volts between our first branch point and the next. And what we found was across R5 was 10 volts. Therefore, 2 plus 10 gets us back to the 12-volt battery supply. So things in series, the voltages should add up eventually back to our battery supply if we collapse everything onto a single path. Things in parallel, the voltages should eventually across one path should equal the voltage drop across the other path, as long as everything is in series on the top path and in series on the bottom path, and then these two paths are in parallel. So the value here for biophysics is that DC circuits, the resistance through a simple resistor DC circuit wonderfully matches resistance through blood vessels, arteries, veins, capillaries, how they branch and how they are in series. That flows wonderfully. Now, if we were to model the nervous system, we actually have more components in that type of circuit, biological circuitry, which can be represented through an RC circuit, a circuit which consists of resistors and capacitors. Looking at our sample problem, we have some battery supply voltage that sends current through two resistors, R1 and 2, that are parallel to each other. And then once they branch back together at a node, we have resistor 3 in series. And then we have 3 capacitors, 1, 2, and 3, that are all in parallel. And once we branch back, we have 2 capacitors that are in series, C4 and C5. Our problems are going to be, if we have a 24-volt power supply, that's the battery, and this was connected to the RC circuit shown above, what would be the following answers? For question 1, we're just going to simplify the circuit to a single resistor and single capacitor and then sketch it. Well, how we're going to do that? Pretty straightforward. We can do this honestly in one step. Let's see. Here we go. If we're going to simplify the resistances, well, we know that R1, R2, they're a single resistor on, they're each just one resistor on parallel paths. So their equivalent resistance would be 1 over R1 plus 1 over R2 raised to the negative first power. And whatever that value becomes, that would be a equivalent resistor in series with R3. So we can just add that to R3. So 4/3 Siemens, or 4/3 inverse ohms plus 2/3 Siemens becomes raised to the negative first power plus 17/2 ohms. This eventually becomes 6/3 Siemens raised to the negative first power plus 17/2 ohms, or 1/2 ohm plus 17/2 ohms, equaling 9/2 ohms of resistance if we had one single resistor in this circuit. So that's how we get 9 ohms for RT. If we were to now look at the conductors, well, or capacitors, I should say, the capacitors. Conductors are the opposite of resistors. Capacitors are a completely different circuit component. Well, the rules are the exact opposite for capacitors. Essentially, if we have a single capacitor on 3 parallel paths, we can just add up their values. So the equivalent capacitance of C1, 2, and 3 would just be adding all of them together. And whatever that one becomes, that would be an equivalent capacitor in series with C4 and C5. Therefore, the sum of C1, 2, and 3, whatever that adds up to, we'll take its reciprocal and add it to the reciprocal C4 and the reciprocal C5 and raise all that to the negative first power. This gives us 1 over 12 farads plus 8 farads plus 4 farads plus 5/12 inverse farads plus 7/24 inverse farads. Simplifying our answers, eventually we get our parallel paths farads to add up to 24, so the inverse would be 1/24 inverse farads. We already have another part of our expression that is over 24, so we can take 5/12 and just make that 10/24 so that everything has the same denominator. That adds up to 18/24 inverse farads, which simplifies to 3/4, and then that becomes, when we invert it, 4/3 farads, and that is our equivalent capacitance if we just put in one single capacitor in our circuit. And if we were to sketch it, well, you would just sketch your power supply, a single resistor, that jagged line, and then a capacitor where we have that 2 plates that are separated in space, and then just write in their symbols and their values. Now, since we have our equivalent resistor and equivalent capacitor, we can solve the remaining 4 problems because they're going to use some constant called tau, the time constant. For question 2, determine the time constant. That's just the equivalent resistance times the equivalent capacitance. We determined that we had an equivalent resistor of 9 ohms and an equivalent capacitor of 4/3 farads. Multiplying those together, we get 12 seconds for our time constant. Just to note, an ohm times a farad is a second. Question 3 would be, if the equivalent capacitor CT was charged for 30 seconds, what would be the voltage drop across the capacitor? The formula is the voltage drop across our capacitor after a certain amount of charging time is equal to, since we're charging it, is equal to the power supply voltage times the quantity, 1 minus E raised to the amount of time we were charging it, divided by our time constant. So only use this formula if you're charging a capacitor. VC, or the voltage drop across our capacitor after 30 seconds, would be the power supply, the original battery, times 24 volts, times 1 minus E raised to the negative 30 seconds over 12 seconds. 30 seconds coming from how long we've been charging it, and 12 seconds being our time constant. And if everything is plugged in correctly, you should get 22.03 volts. For question 4, how much time would need to pass to charge the capacitor CT to 60%? Well, the nice thing is, as a percentage, we don't need our voltage of our battery supply. We just need, since the charging time is actually relative to our time constant, all we need is To calculate the amount of time it takes to charge a capacitor to a certain percentage, that's going to be negative tau times the natural log of 1 minus a simply being our percentage in decimal form. So t equals negative 12 seconds times the natural log, or log base e, of 1 minus 0.6, the 0.6 coming from 60% charged. That's approximately 10.9955 seconds, which, give or take, you can round that to 11 seconds. Although for your exams, if you're typing an answer in Blackboard Learn, put in a bunch of decimal places as much as you're comfortable with, at least up to 6 or 8. Now, question 5. The capacitor CT was fully charged to 24 volts. What would the voltage drop across the capacitor be after it was discharged for 17 seconds? Now, we're not charging it with our power supply. We are now discharging it. That means we'll use this formula. The voltage drop across our capacitor after a certain amount of time is V naught, V nil, which is how much voltage did we charge it to, times e raised to the negative t over tau. Now, if you ever hear in this type of sentence, you charge the capacitor fully, just assume you charged it to the original battery supply. So if it was 18-volt battery supply, if your problem just says it was fully charged, then just put in 18 volts for V0. However, this does not have to equal the battery supply. For example, let's say our capacitor was, if our battery supply is 24 volts, but maybe you're told it was only charged to 20 volts. Then if it was only charged to 20 volts before discharging, you would plug in 20 here. So if we calculate the voltage across our capacitor after 17 seconds of discharge, what we get is that 24 volts that we got it up to before discharging times e raised to negative 17 seconds over 12 seconds, which if that's plugged in all correct, you should get an answer of 5.82 volts. In any case, that concludes this week's recitation. Send in questions if you have any, and as always, peace.